Now let's turn the focus back on the Amish people and their particular Pi1 deficiency mutation. So first, who are the Amish people, right? The Amish are a group of traditionalist Christian communities that are known for their simple living, plain dress, and also reluctancy to adopt modern technology. So I guess you can say they're, back in the old day kind of folk. They originated from the Anabaptist movement in Europe in the 16th century and then migrated to North America in the 18th and 19th centuries to escape religious persecution. Now, this isn't a politics video, this isn't a historical video, but we have to give a sort of context to these people. The Amish tend to live in rural areas and maintain a lifestyle centered on farming, family, and community, and they often reject modernity in general. But also, they're very, very closed off to the outside world. So this leads to cool things where they have a distinct dialect called Pennsylvania Dutch, which is derived from German, and Pennsylvania is a state in the United States. It's on the East Coast, heading towards Ohio, but these sort of Amish communities tend to be very, very secluded from the outside world, and it leads to them having significant rates of inbreeding. And with inbreeding, you start to get these weird genetic abnormalities and mutations. Now, the Amish have certain rare genetic disorders, some serious, some odd, and just some quite cool. One is maple syrup urine disease, where it essentially, their piss, their urine, kind of smells like maple syrup. But this disease affects metabolism, right? And there's also sort of associated issues with that as well, like infections. And if left untreated, maple syrup urine disease can actually become fatal. So these people typically have to eat a low protein diet. The Amish also have a higher rate compared to the general population of individuals that have polydactylism, where people have extra fingers or extra toes. But what I find to be more interesting out of all these sort of random mutations is the Pi1 deficiency, which is relatively common, or at least common enough in the Amish population such that this results in Amish people living, on average, longer than the general population. The research mentioned from Northwestern University, detailed in Maria Paul's article, explored the positive consequences of this Pi1 deficiency mutation. Now, the literature seems to point to that in Amish populations, because they have a prevalence of people that have a Pi1 deficiency, this results in the overall Amish populations tending to live 10% longer than the general population. It was also found that people that had the Pi1 deficiencies have longer telomere caps, which are protective caps on chromosomes that safeguard DNA from damage during duplication and other sort of factors of oxidative stress. Furthermore, they also had lower fasting insulin levels and greater vascular flexibility, which are known markers of reduced biological aging. So I said all of that to tell you what, right? What is the takeaway from all of what I described from the Amish people? Well, these findings suggest that reduced Pi1 levels slow down cellular aging by preserving telomeres and decreasing the burden of senescent cells. This mechanism appears to create a systemic benefits, including better cardiovascular health, reduced diabetes risk, or rather type 2 diabetes risk, and potentially an enhanced regenerative capacity as seen in clinical studies where Pi1 inhibition seemed to reverse aging-related changes. However, this was of course seen in mice, and also in these same mice, we saw factors of hair growth as well, right? But what we can see is that because we have Pi1 inhibition in these Amish people, we get the understanding that, okay, it's the integrity of those telomeres and keeping those telomeres healthy that seems to keep other sort of bodily functions in check and relatively young in terms of cellular age. So carrying that sort of understanding to hair follicles, right? What is hair loss but just the aging of a hair follicle? We'll touch on this later on in the video when we talk about the relations between telomeres and hair follicle stem cells, but mostly I just want you guys to just, keep that in mind for now. Because right now we're going to get a bit morbid, so forgive me if I become morbid here, but we're going to be looking at a syndrome called Werner syndrome. Now, the pictures themselves may be a bit off-putting, so, try to skip to a later point in the video. I do encourage you to, if you're watching it, actually watch the video, but if not, if you don't want to be like too disturbed, maybe just play it in the background or whatever, right? But I'm just going to kind of warn you guys because, I've just looking at this myself, it kind of made me feel a bit unsettled. But anyway, if we reduce Pi1 then as we see in the Amish people, it should sort of protect against aging. Aging of all cell types, perhaps. There's a condition called Werner syndrome, also known as adult progeria. Now, if you're familiar with progeria, you may know that it's a condition in which rapid aging occurs. This condition occurs more so in infants and children than in adults or teenagers, and the common progeria that we see is called Hutchinson-Gilford progeria syndrome, and like I said, it impacts children. However, Werner syndrome impacts adults or teenagers, so this is where we kind of get a bit, dark with things. Now, where's the connection between the Pi1 protein and Werner syndrome? Well, according to the review article titled, quote, Plasminogen Activator Inhibitor 1 is a marker and mediator of senescence, unquote, by Ghosh et al., it is noted that with age, elevation of Pi1 levels occur, and this dictates the onset progression of age-related diseases like atherogenesis, which is the formation of fatty plaques in the arteries, thrombosis, also being blood clotting, and of course this is typically seen in elderly populations, but also, more importantly, people with Werner syndrome. Because again, may I remind you, Werner syndrome is just premature rapid aging that occurs shortly after puberty. And I'll put some pictures over here, right? We have this 15-year-old girl that, at 48 looks like she's 95. So there's possibly a high amount of Pi1 activity, a large amount of senescent cells occurring rapidly, and it gives us the understanding about how high Pi1 levels just seem to age the body and age the cells. But aging occurs when you essentially have had multiple cell cycles, right? When there's multiple cycles of cell division, proliferation, apoptosis, so on and so forth. But each time a cell duplicates, divides, and then dies and goes through that process over and over again, the telomeres become shorter and shorter. And of course, we become older and older, things start to break down. So if we apply that to the hair follicle biology, as there are more anagen cycles, slowly but surely, those telomeres in the hair follicle stem cells, they kind of shorten, right? And because of that, even potentially with people that don't have androgenetic alopecia, they can get something called senile alopecia, where this is a hair loss that occurs with age, where every hair follicle only has so many cycles that it can grow through. And other alopecia conditions like androgenetic alopecia or even scarring alopecias like lichen planopilaris also sort of influence those telomere lengths and kind of rapidly age up those hair follicle stem cells. And it also shortens the amount of what? Anagen cycles, growth cycles that hair follicle can go through. So with that in mind, it appears that controlling for cellular senescence, because senescence leads to secretions that age up telomeres by causing those telomeres to shrink, and it seems that the presence of Pi1 increases the amount of senescent cells that one may have. Reducing that senescence may be beneficial and could help hair follicle stem cells have their telomeres protected, along with keratinocytes and melanocytes, or those cells that give your hair its pigment. This, on the other hand, would help reduce instances of gray hair and balding. And this is exactly what Irion Therapeutics is trying to do with ET02 as well as ET03. You see, because if you can protect those telomeres, you can slow down hair loss and the cellular aging of that hair follicle. So this is an instance where Pi1 inhibition can protect hair follicle stem cells by targeting senescent cells that could be influencing toxic lipid accumulation.